Another application of constraint optimization is when we want to minimize the cost of producing multiple outputs. In this case, we want to minimize the production cost of X and Y, subject to a resource constraint. Here U, X, and UY means how much labor I will use to produce 1 unit of X and to produce 1 unit of Y. In this particular case, we will have also an interesting property in which we have that the marginal cost ratios are equals to the ratio of the labor usage for both outputs. And as before, the Lagrange function is simply the objective function, which in this case is the cost function, minus lambda times the resource constraint, in which, remember, we have to have it equals to 0. Let's illustrate how we solve a cost minimization problem with multiple outputs by solving the following example. Yusef is a manager in the Fraser firm. The firm produces two goods, wood tables and mirrors. Both are labor-intensive goods. A wood table requires 4 hours of labor, and the mirrors require 6 hours of labor. Considering that he has 35 employees that work 8 hours every day, he wants to know the optimal allocation of output that minimizes the cost given the following cost function. And then he wants also to know what is the optimal cost. In this cost minimization problem, we have the cost function subject to a resource constraint. The quantity of hours per wood table is 4, and the quantity of hours to produce mirrors is 6. And we have 35 employees that work 8 hours every day. So that is equals to 280 hours available. Now that we have our Lagrange problem, let's set up the Lagrange function. In order to set up our Lagrange function, remember that we have to have 0 in one of the sides. So here we can subtract 4x to both sides and 6y to both sides. So we will have 280 minus 4x minus 6y. So this will be our restriction. So for the Lagrange function, remember that we need the objective function minus the lambda times the restriction. And this must be equals to 0. In this case, the Lagrange function will be then the objective, which is the cost function, minus lambda times the restriction, which is 280 minus 4x minus 6y. And again, the Lagrange has 3 variables, x, y, and lambda. Let's obtain the first order conditions. With respect to x, this is 72x minus, here the constant part is 12y, and the derivative of x with respect to x is simply 1. Plus 0 minus lambda times the derivative with respect to x is simply minus 4. And this is equals to 0. Now the Lagrange with respect to y. So here we have minus 12x and then plus 82y. The first one is 0 because it does not contain y. Minus lambda times the derivative with respect to y is simply minus 6. And we set this equals to 0. And finally we have Lagrange with respect to lambda. So this is minus 1 times 280 minus 4x minus 6y. And this is because the derivative of the Lagrange function with respect to lambda only appears here, so the derivative of lambda with respect to lambda is 1. And now let's rearrange a little bit here. So from this one, we obtain that 72x minus 12y is equals to minus 4 lambda. And here, minus 12x plus 82y is equals to minus 6 lambda. And here we obtain the original constraint. So let's divide equation 1 by equation 2. So from here, you can notice that the negatives and the lambdas disappear. And then we have two fractions, which means that we can multiply each other. So here we will have 72x minus 12y times 6 must be equals to minus 12x plus 82y times 4. Now 72 times 6 is 432x minus 72y equals minus 48x plus 328y. So this is 480x equals 400y. We can divide, first we can cancel 1 0, and then let's divide everything by 8. So from here, you can see that 6x is equals to 5y, or x is equals to 5 over 6 times y. And then we will use that relationship here. So 280 is equals to 4 times, instead of x, we replace it with 5, 6y plus 6y. So this is 280 equals, this is 20 divided by 6 or 10 divided by 3. And then this is 280 equals, this is 18 divided by 3, so this is 28y divided by 3, which means that y is equals to 30. And x then will be 5 over 6 times 30. This is going to be equals to 25. In other words, x is 25 and y is equals to 30. And now we can find the optimal cost. Remember that the function was 36x squared minus 12xy plus 41y squared. So this is going to be 36 times 25 squared minus 12 times 25 times 30 plus 41 times 30 squared. The optimal cost then will be 50,400.